Okay, so a lot of the problems this week deal with a very specific situation, and the very specific situation we're dealing with is constant acceleration in a straight line. Now, here's a velocity versus time graph, and on a velocity versus time graph, acceleration is the slope. So I hope you can see that this is not an example of constant acceleration because the slope of the line here is different from the slope of the line here, is different from the slope of the line here. So if an object were to move like this, it would not be constant acceleration, and all of the equations that we're going to talk about in this video would be useless. That being said, there is a region of this graph where the acceleration is constant, and that would be the part of the graph where there's a nice straight line. So if we were to start here and end here, we would be looking at an example of constant acceleration. So that's what I want to do. I want to look at just that portion of the graph. So when we do that, we say, okay, this is 0. That is when the time is equal to 0. That's going to be our starting time. And this is going to be our ending time. So this is going to be when t is equal to the final time, t. The slope of this line is the acceleration. And this is the initial velocity, the starting velocity of the object, and this is the final velocity, the ending velocity of the object. And we can develop several equations that help us describe motion with constant acceleration. And I'm going to do that two ways. I'm going to start with calculus. So if we say that acceleration is constant, what we can do is we can integrate that. Velocity as a function of time is equal to the integral of acceleration as a function of time. But since the acceleration is constant, we are just integrating a constant. And when you integrate a constant, what you get is that this is equal to acceleration times time plus some undetermined constant. And now we can figure out what that constant should be by plugging in t equals 0. If I plug in t equals 0, I find out that at goes to 0, and the velocity at t equals 0 should equal the initial velocity of the object. So we end up with this equation that says the final velocity of the object is equal to the initial velocity of the object plus acceleration times time. And that would be our first equation that's true for constant acceleration. Next, to find position, we can integrate again. And if we integrate again, we can find that our position should be equal to the integral of velocity. And again, this is just a polynomial. So when we integrate v0, we get v0 times time. When we integrate at, we get 1/2 at squared. And then we add our constant. And this would be our position as a function of time. And then if we plug in t equals 0, we find out that this constant should be the initial position. So what we end up with is that the final position is equal to the initial position plus v0t plus 1/2 a t squared. And what I do is I subtract x0 from both sides. So we end up with x minus x0, final position minus initial position, is equal to v0t plus 1/2 at squared. And this x minus x0, that's the final position minus the initial position, we call that the displacement of the object. And this would be our second equation. Okay, and that's using calculus to derive those two equations, but I also would like to do it just looking at the graph. So if I look at this graph, if I want to know the displacement, what we learned in previous videos is that displacement is the area under the curve. So if I break this up into a rectangle, this rectangle has an area of v0 times t. And then the triangle has an area of 1/2 base times height. So that's equal to, the area of this is equal to 1/2 the base, which is t, times the height, which is equal to v minus v0. Yeah, I did that right. Okay. So we can do two things with that. We can say, okay, that just means that the displacement is equal to v0t plus 1/2, and I'll distribute this, 1/2 vt minus 1/2 v0t. And then this simplifies into displacement is equal to 1/2 v0 plus vt. Okay, but that's actually a new equation. Let's hold on to that one. You can write it down in your notes, but let's just hold on to that one for a minute. I want to write this slightly differently. V minus v0 is okay. I did the order of this poorly. Let's look at the slope first. Slope is rise over run. So acceleration should be the rise, that is v minus v0, divided by the run, that is t. So I can rearrange this equation and get that v is equal to v0 plus at, which is the same equation that we got by integrating. But I can also rearrange this equation and get that v minus v0 is equal to at. So this v minus v0 is equal to at. So if I do 1/2 t times at, that gives me that displacement is equal to v0t plus 1/2 a t squared, and that's my second equation. So we can do this using calculus to figure out the two constant acceleration equations, or we can do this using a graphical method by looking at the graph to get these two constant acceleration equations. Either way, these two equations, I'll write these down as number one, final velocity is equal to initial velocity plus acceleration times time. Equation 2, displacement is equal to initial velocity times time plus 1/2 acceleration times time squared. Those two equations can be used to solve any constant acceleration problem. And they can only be used when we know the acceleration is constant. That is, when the slope of the velocity versus time graph is a straight line. Okay, and these two equations are great, and we can do everything we need with those two equations. And you can fast forward through the next couple minutes of this video. I'm going to just do some algebra, because oftentimes it's helpful to combine these equations in different ways. So the first way I can combine these two equations is to solve the first equation for acceleration, and I get that acceleration is equal to v minus v0 over t, and I can substitute that into the second equation, and that gives me displacement is equal to initial velocity times time plus 1/2 acceleration times, so for acceleration, I'm going to substitute v minus v0 over t. So 1/2 v minus v0 over t times t squared. Now here, one of those t's cancels with that t, and this becomes displacement is equal to v0t plus 1/2 vt minus 1/2 v0t. And then here, if we subtract half v0t from v0t, we get displacement is equal to 1/2 v0t plus 1/2 vt. And if I write that one more time, I can collect the 1/2 and the t, can pull the 1/2 out in front, pull the t out behind, and what I'm left with is initial velocity plus final velocity, and that is my third equation. Displacement is equal to 1/2 initial velocity plus final velocity times time. And we got that graphically, sort of by accident, but also I want to show you what that means graphically. Whereas this equation is a rectangle plus a triangle, this rectangle here plus this triangle here. Equation 3 is actually the equation for a rectangle with a height that's equal to the average velocity and a base that's equal to the time. So let's see what that looks like here. If I take halfway between the maximum, the starting velocity and the finishing velocity, and I make a rectangle, the area of this rectangle, this little triangle here fits exactly with that little triangle there, so the area of this rectangle is the same as the area under the curve. Okay, and then the last equation is, instead we're going to solve this equation for t. So we solve equation 1 for t. So t is equal to v minus v0 over a, and substitute that into equation 2. So displacement is equal to v0 times v minus v0 over a plus 1/2 a times v minus v0 over a squared. So this becomes d is equal to, I'm going to distribute the v0, v0 times v over a minus v0 squared over a. Okay, and for this one, we've got to FOIL out the top. So let's keep the 1/2 a. And v minus v0 squared is v squared minus 2v v0 plus v0 squared all over a squared. And this a cancels with that a. One more line, v0 v over a minus v0 squared over a plus 1/2 v squared over a minus v0 over a plus 1/2 v0 squared over a. Now, this term and this term cancel. Okay, and this term and this term don't cancel, but here I have negative v0a, and here I have 1/2 v0 squared over a. Sorry, I got negative v0 squared over a and plus 1/2 v0 squared over a. Those combine and give me d is equal to negative 1/2 v v0 squared over a, and then I'm left with this last term here, plus 1/2 v squared over a. And now I'm just going to multiply the entire equation by 2a. So 2ad is equal to v squared minus v0 squared. And this gives us our fourth equation, that v squared is equal to v0 squared plus 2ad. And these four equations are the ones that we will be using to solve constant acceleration problems. And they come from these two equations, which we can get either from calculus or from looking at a graph of velocity versus time.